Welcome to today's session. In this video, we'll be tackling LeetCode problem number 679, titled 24 Game. This is an engaging mathematical problem that challenges us to use four numbers in basic arithmetic operations to arrive at the target value of 24. Let's dive in and explore the approaches to solving this puzzle. To tackle the 24 game problem, let's first consider the brute force approach. The intuition here is straightforward. We evaluate all possible permutations of the four given numbers, which amounts to 24 permutations in total since there are 4 factorial ways to arrange them. For each permutation, we then explore all possible combinations of arithmetic operations: addition, subtraction, multiplication, and division applied in every conceivable order. This requires simulating all potential parenthesizations of the expressions, as the order of operations profoundly impacts the result. For example, adding two numbers and then multiplying the result by a third yields a different outcome than multiplying two numbers first and then adding. While this approach guarantees coverage of all possibilities, it is computationally expensive due to its exhaustive nature. A more sophisticated method involves optimized recursive backtracking. The key insight here is that instead of treating the problem as one large computation, we can break it down into smaller subproblems. At each step, we select two numbers, perform an operation, and replace those two numbers with the result. This reduces the number of elements we're working with from 4 to 3, then to 2, and ultimately 1. If the final number is 24, or close to it within a small margin to account for floating point precision, we know the solution works. By pruning paths early, such as discarding those that produce unrealistic results or duplicate combinations, we drastically limit unnecessary exploration. For instance, recognizing that addition is commutative allows us to avoid evaluating both A plus B and B plus A, as they yield the same result. This approach is more strategic and efficient than brute force because it focuses only on viable paths and systematically narrows the problem space. In addition to recursive backtracking, alternative heuristics can sometimes be applied to further optimize the process. For example, we might prioritize certain operations, such as multiplication or division, based on their impact on the result. Similarly, focusing on integer-only computations in intermediate steps can occasionally help streamline the solution. However, these heuristics tend to be more specific to certain input scenarios and are not universally applicable across all cases. The approach we ultimately chose is recursive backtracking, and it stands out as the most effective strategy for this problem. What makes it ideal is its systematic exploration of all potential combinations of numbers and operations while allowing early pruning of unviable paths. Unlike brute force, which indiscriminately evaluates every possibility, backtracking dynamically reduces the problem size with each step and avoids redundant calculations. This ensures that the solution remains efficient without compromising on correctness. Of course, there are trade-offs. While brute force guarantees accuracy through sheer exhaustiveness, it is computationally prohibitive due to its high redundancy. Recursive backtracking is far more resource efficient, but it demands careful attention to floating point arithmetic. Using an epsilon value, such as 1 times 10 to the power of -6, helps mitigate the risk of rounding errors and ensures reliable comparisons between floating point results. Finally, let's consider the complexity of these approaches. For the brute force method, the complexity arises from evaluating all 24 permutations of the numbers, combined with the nested operations required for each permutation. This results in a time complexity of 24*4 cubed, which is clearly infeasible for larger scale problems. On the other hand, recursive backtracking achieves significant improvements by pruning unnecessary paths and avoiding redundant computations. While the exact complexity depends on the constraints of the input, the efficiency gain from early termination and reduced problem size is substantial. In summary, recursive backtracking strikes a balance between thoroughness and computational efficiency, making it the preferred approach for solving the 24 game problem. By focusing on viable solutions and leveraging pruning techniques, we can solve the problem more effectively while ensuring the results remain accurate. This balance is why recursive backtracking is the strategy of choice for this challenge. The problem challenges us to determine if we can combine four given numbers using basic arithmetic operations: addition, subtraction, multiplication, and division to achieve a target value, which is typically 24. To solve this, we need to evaluate all possible ways the numbers can be arranged and all possible combinations of operations that can be applied to them. This requires us to explore permutations of the numbers and test every sequence of operations. For example, if the numbers are 4, 1, 8, 7, we must check if any arrangement of these numbers, combined with any sequence of operations, leads to 24. Additionally, we must account for constraints, such as using each number exactly once and avoiding invalid operations like division by 0. To begin, we need to generate all permutations of the 4 numbers. Since the order in which the numbers are combined affects the result, we must evaluate every possible arrangement. There are 4 or 24 permutations of 4 numbers, which ensures we cover all potential sequences. Python's itertools.permutations is a highly efficient way to generate these permutations, making it a practical choice for this step of the algorithm. Now that we have all permutations of the numbers, the next step is to evaluate all combinations of operations. Between any 4 numbers, there are 3 slots where operations can be applied, and each slot can hold one of 4 operations: addition, subtraction, multiplication, or division. This gives us 4 cubed, or 64, combinations of operations for each permutation of numbers. By systematically iterating through these combinations, we ensure that every possible way of applying operations is tested. Next, we need to consider the different ways the operations can be grouped. This involves using recursion to evaluate all possible groupings of numbers and operations. For instance, we could first combine the first 2 numbers with an operation, then recursively process the result with the remaining numbers. Alternatively, we could group the last 3 numbers first and then combine their result with the first number. This recursive approach allows us to explore all possible ways of bracketing the expressions, which is crucial for finding the correct solution. As we proceed, we must handle special cases like division. Specifically, division by 0 is undefined, so we need to skip any operation where the denominator is 0. Finally, for each combination of numbers, operations, and groupings, we check if the result matches the target value, which is 24 in this case. Due to floating point precision issues, exact equality checks may fail, so we use a small tolerance, such as 1 times 10 to the power of -6, to account for rounding errors. This problem highlights several key insights that are critical for an efficient solution. First, the combination of permutations and operations introduces significant complexity, as we need to test all possible arrangements of numbers and all sequences of operations. Utilizing optimized libraries like itertools for generating permutations reduces implementation overhead and ensures efficiency. Second, recursion is essential for handling arbitrary groupings of numbers and operations. By recursively exploring all possible ways to bracket the expressions, we ensure no valid grouping is overlooked. Third, floating point precision can pose a challenge when comparing results to the target value. Using a small tolerance instead of direct equality checks helps account for minor discrepancies caused by rounding errors. On the data structure side, the algorithm relies on lists to store the 4 numbers, a permutations generator from itertools to generate all possible orderings, and the recursive function call stack to manage the exploration of groupings. In terms of complexity, the time complexity includes generating permutations, which is O(4) or O(24), and evaluating operations, which involves 4 cubed or 64 combinations for each permutation. The recursive evaluations for groupings add additional overhead, but since we only have 4 numbers, the total complexity remains manageable. The space complexity is primarily driven by the recursion stack, which depends on the depth of recursive calls, up to a maximum of 4 levels. Together, these insights and analyses provide a comprehensive understanding of the algorithm's structure and its computational requirements. Here, we begin by importing the permutations function from the itertools module, which will help us generate all possible orderings of the input numbers. Then, we define a class called solution and within it, a method named judgePoint24. This method takes a list of numbers, nums, as input. Inside, there is a helper function designed to recursively evaluate all possible combinations of numbers and operations. The first check in the helper function is to see if the array has only 1 number left, and if that number is close enough to 24, within a very small margin of error. If so, it returns true. Next, we use a nested loop to iterate over all pairs of numbers in the array. For each pair, we create a new array, next_rr, which contains the remaining elements after removing the selected pair. Then, we try all possible operations between the two numbers: addition, subtraction, multiplication, and division. Division is only performed if the second number is not 0 to avoid errors. After applying an operation, the result is appended to the next_rr, and the helper function is called recursively to evaluate this new state. If the recursive call to the helper function with the updated array returns true, it means we have found a way to calculate 24, and so we can immediately return true. If not, we backtrack by removing the last appended operation result to explore other possibilities. If no valid operations or combinations lead to 24, the helper function ultimately returns false. Back in the main method, we then iterate over all permutations of the input numbers using the permutations function. This ensures that we account for all possible orderings of the numbers, as the order of operations can affect the outcome. For each permutation, we convert it to a list and pass it to the helper function. If any permutation leads to a result of 24, the method returns true. If none of the permutations yield 24, the method finally returns false, indicating that it is not possible to achieve the target value with the given numbers. Here, we start our Java implementation of the 24 game problem. The solution begins with the judgePoint24 method, which takes an array of 4 integers as input. These integers represent the numbers we need to manipulate to reach the target value of 24. The first step is to convert these integers into a list of doubles. This is necessary because some operations, such as division, will result in non-integer values. Once the list is prepared, we call the helper method, which will handle the recursive logic to explore all possible combinations of operations. Inside the helper method, the base case checks if there is only one number left in the list. If so, we compare it to 24, allowing for a small margin of error using the condition math.abs, list.get 0, 24, 1e6. This accounts for potential floating point inaccuracies. If the condition is true, the method returns true, indicating that 24 can be achieved with the given numbers and operations. Now, if the list has more than one number, we enter a nested loop to iterate through all pairs of numbers in the list. For each pair, we create a new list called next that excludes the current pair of numbers. This ensures that we focus on the remaining numbers after performing an operation. We then retrieve the values of the selected pair, A and B, and explore all 4 possible arithmetic operations: addition, subtraction, multiplication, and division. For each operation, we calculate the result and add it to the next list. Importantly, for division, we check if the divisor, B, is not 0 to avoid a division by 0 error. After each operation, the helper method is called recursively with the updated list. If it returns true at any point, we know that achieving 24 is possible, so we return true immediately. If not, we backtrack by removing the last operation's result from the next list, ensuring the state is reset for the next iteration. Finally, if the recursive exploration completes and no valid sequence of operations leads to 24, the method returns false. This indicates that it's not possible to achieve the target value with the given numbers and operations. The combination of recursion, backtracking, and floating point precision handling ensures that all possibilities are explored efficiently while avoiding errors like division by 0. This completes our Java implementation of the solution. To solve the 24 game, we start with an example where the input array is 4, 1, 8, 7. The first step is to generate all possible permutations of this array, and one such permutation is 4, 1, 8, 7. From here, we begin exploring combinations of operations recursively. First, we pick 2 numbers, 4 and 1, leaving 8, 7 as the remaining numbers. We try all 4 operations with 4 and 1. Adding them gives 5, so we proceed with the array 5, 8, 7. Subtraction results in 3, leading to 3, 8, 7. Multiplication gives 4, and division also yields 4, both resulting in 4, 8, 7. Next, we explore one of these paths, such as 5, 8, 7, from the addition operation. Here, we pick 5 and 8, leaving 7 as the remaining number. Again, we try all operations, adding gives 13, so we proceed with 13, 7. Subtraction gives -3, leading to -3, 7. Multiplication results in 40, and division yields 0.625, producing 47 and 0.6257, respectively. Continuing with 13, 7, from the addition path, we test all operations. Adding gives 20, subtracting results in 6, multiplying yields 91, and dividing produces approximately 1.857, none of which equal 24. At this point, we need to backtrack to explore other combinations. Now, the algorithm systematically backtracks and explores other combinations of numbers and operations. For instance, when using the permutation 8, 7, 4, 1, and applying the operations 8/open parenthesis 7 minus open parenthesis 4 divided by 1 close parenthesis, we achieve the exact result of 24. At this point, the function returns true for this input, as a solution has been found. In a second example, the input array is 1, 2, 1, 2. Just as before, we generate all possible permutations, one of which is 1, 2, 1, 2. We start by picking 1 and 2 and test all operations. Adding them gives 3, leading to 3, 1, 2. Subtraction results in -1, producing -1, 1, 2. Multiplication gives 2, and division yields 0.5, leading to 2, 1, 2, and 0.5, 1, 2, respectively. 4, 3, 1, 2, from the addition path, we pick 3 and 1 and explore further. Adding these numbers produces 4, giving 4, 2. Subtraction results in 2, and both multiplication and division yield 3, leading to 2, 2, and 3, 2. Finally, with the 4, 2, we test all operations. Adding results in 6, subtracting gives 2, multiplying produces 8, and dividing yields 2. None of these results equal 24, so the algorithm continues exploring other combinations. After thoroughly exploring all possible combinations for the input 1, 2, 1, 2, no solution is found that results in 24. Therefore, the function returns false for this input. Finally, consider a third example with the input array 3, 3, 8, 8. As always, we generate all permutations, such as 3, 3, 8, 8. By recursively exploring operations, a valid combination is found. For instance, using the expression 8/open parenthesis 8 minus open parenthesis 3 divided by 3 close parenthesis, we achieve exactly 24. Since a solution exists for this input, the function returns true. This example highlights the importance of systematically testing all possible permutations and operations to ensure no valid solution is overlooked. To analyze the time complexity of our solution, we need to consider two main components: the generation of all permutations and the recursive evaluation process. First, let's look at permutations. Since the input list always contains exactly 4 numbers, the number of permutations we can generate is fixed at 4 factorial, or 24. This means the time complexity for generating permutations is 24, which is constant and does not grow with the input size. This forms the first part of our analysis. Now, turning to the second component, the recursive evaluation. At each step, the solution selects 2 numbers from the list and evaluates all 4 possible arithmetic operations: addition, subtraction, multiplication, and division. After performing one operation, the list size decreases by 1, and the recursion continues until only one number remains. The number of recursive calls depends on how the operations are grouped. For 4 numbers, there are multiple ways to group these operations, resembling the pattern of Catalan numbers. For this specific case, the total number of recursive calls amounts to 5 factorial, or 120. Combining the 2 components, we generate permutations in 24 time and recursively evaluate each permutation in 120 time. This results in an overall time complexity of 24 by 120, which simplifies to 2880. Since the input size is fixed at 4, this is a constant time solution. However, for variable input sizes, the time complexity grows exponentially as n asterisk 4 caret n1. Now let's evaluate the space complexity. The first factor to consider is the recursion call stack. The depth of the recursion corresponds to the number of elements in the input list, starting with 4 and reducing to 1. This means the maximum depth of the call stack is 4. Each recursive call maintains temporary variables for the current state of the list and the operation being performed, leading to a space usage of O, n, where n equals 4. Next, we account for the storage of permutations. Generating all permutations requires O24 space, which is constant and does not scale with input size. Finally, an auxiliary list next _RR is created at every recursive step to represent the remaining numbers. Since the size of this list decreases with the recursion depth, the space required for it is also proportional to n, or 4. Combining these factors, the total space complexity is dominated by the recursion call stack and the auxiliary list, resulting in O, n, which simplifies to O, 4, for our fixed input size. To put this into perspective, let's compare the current approach with a naive brute force method. A brute force solution would involve trying every possible grouping, ordering, and sequence of operations. This results in an exponential time complexity, similar to our current approach, but without the efficiency gains. The current solution improves upon brute force by pruning invalid paths early, such as skipping divisions by 0 or stopping recursion when the target can no longer be reached. The time complexity of O, n. *4 n1 is derived from generating n permutations of the input list and evaluating 4 operations at each step, leading to 4 n1 recursive evaluations. For n equals 4, this simplifies to O24 by 120, or O2880, which is manageable due to the fixed input size. In terms of best and worst cases, the runtime remains O2880, in the worst case due to the exhaustive nature of the search. However, in the best case, the solution may find a valid permutation and operation sequence early, pruning much of the recursion tree. The space complexity, on the other hand, remains consistent across cases, as the maximum call stack depth is fixed at 4. To summarize, the time complexity of this solution is O, n. *4 n1, which simplifies to a constant O2880, for n equals 4. The space complexity is O, n, or O4, for the fixed input size, driven primarily by the recursion call stack and auxiliary lists. This approach achieves optimization over naive brute force by employing pruning techniques to eliminate unnecessary computations. Together, these factors make the solution efficient and well suited for the constraints of the problem. When solving problems like the 24 game, it's important to avoid some common mistakes that can lead to incorrect results or runtime errors. First, be cautious about how integer division is handled in your programming language. For instance, in Python, dividing 3 by 2 gives 1.5 as a floating point result, whereas in Java, using integer division would produce 1. Always ensure your implementation accounts for these differences, especially when switching between languages. Next, operator precedence is another frequent pitfall. Arithmetic operations follow specific rules, where multiplication and division take precedence over addition and subtraction. So, an expression like 3 plus 4 times 2 would be evaluated as 3 plus the result of 4 times 2, not 7 times 2. Explicitly using parentheses can help you avoid these types of errors. Lastly, floating point precision can be tricky. For example, adding 0.1 and 0.2 may not yield exactly 0.3 due to how decimals are represented in binary. To compare such results, it's better to use functions like math.isclose in Python, which allow for small tolerances in precision. These details, while subtle, can significantly affect your solution's correctness. Now, let's talk about handling edge cases and optimizing your approach. Edge cases are critical to consider. For example, dividing by 0 will result in errors, so you need explicit checks to avoid such situations. Similarly, think about scenarios involving the smallest or largest possible inputs, or even duplicate numbers, as these can expose flaws in your logic. Inefficient brute force implementations are another challenge. A naive approach might explore all possible combinations without pruning invalid paths, resulting in redundant computations. For instance, recalculating the same subproblem multiple times instead of caching results can significantly slow down your solution. To address this, it's useful to think in terms of backtracking or dynamic programming. Backtracking allows you to explore possible combinations while pruning paths that cannot lead to valid results. Dynamic programming, on the other hand, helps by storing intermediate results to avoid redundant calculations. Additionally, remember the importance of recognizing patterns in these problems. For example, operations like addition and multiplication are commutative, meaning their order doesn't matter, which lets you reduce the number of permutations you need to consider. Finally, always validate your logic with simple test cases, such as inputs of all ones or zeros, before moving on to more complex scenarios. This step can save you from hours of debugging later. There are several related problems that can help you strengthen your understanding of the techniques used in the 24 game. First, the 24 game itself, LeetCode problem 679, is a classic example of applying backtracking to evaluate combinations of numbers and operators. Another related problem is LeetCode 50, which focuses on efficiently computing power functions. This problem emphasizes arithmetic optimization and can teach you how to reduce computational complexity in mathematical operations. Next, LeetCode 241, different ways to add parentheses, is particularly relevant because it explores all valid ways to evaluate an expression by varying the placement of parentheses. This is similar to the idea of exploring permutations of operators in the 24 game. Finally, LeetCode 282, expression add operators, is a variation that involves generating valid expressions to evaluate to a target value. These problems share common strategies, such as using recursion, handling operator precedence, and pruning invalid states, making them excellent practice for refining your problem-solving skills. When tackling problems like the 24 game, there are alternative approaches you can consider, each with its own trade-offs. Backtracking with pruning is highly effective because it reduces computational overhead by avoiding redundant explorations. However, designing the pruning conditions requires careful thought to ensure you're not accidentally eliminating valid solutions. Another approach is dynamic programming, which excels at problems with overlapping subproblems. By storing intermediate results, you can avoid repeated calculations, though this method typically uses extra space for memoization. It's especially useful when the problem's structure allows for breaking it into reusable subproblems. Lastly, iterative permutation generation can be a straightforward alternative. While it's simpler to implement, it may not be as intuitive for problems requiring recursive exploration or hierarchical evaluation of expressions. Choosing the right approach depends on the problem constraints and the trade-offs you're willing to make between computational efficiency, memory usage, and implementation complexity. Great work! We've successfully solved the 24 game and gained valuable insights into problem-solving strategies. Remember to practice recursion and backtracking, as they're powerful tools for tackling similar challenges. Don't forget to like, share, and subscribe to stay updated with more coding tutorials. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!